onto our talks. These are the 100-minute session that we've got booked this afternoon for the Science Perl talks. And our first speaker this afternoon is Dr. Louis Mochán from the Institute of Physical Sciences at the National Autonomous University of Mexico. And he's been simulating metamaterials using Photonic in Perl. So he's going to talk about his Photonic software. So over to you, Dr.
Okay,
Mochán.
first of all, I want to thank William Braswell for the invitation to present my work here, and Andrew Mail, Greg Straight, and all the organizers and volunteers, and all of you present. This is the list of collaborators: Andrea López Reina, Raksha Singla, Lucila Juárez, José Samuel Pérez, Bernardo Mendoza, Guillermo Ortiz, and Mochán too, which suggested improvements, contributions, suggestions, etc. And this work has been financed by the National University of Mexico, and this is the grant number. So what I want to talk is about a package we call Photonic. So what is this package? It's a package to compute the optical properties of metamaterials and photonic crystals. It's in the public domain. You can find it in GitHub and CPAN. And it was built using PBL, the Perl language, the PBL Perl data language numerical extension, and the object system loop. So what is a metamaterial? A metamaterial is a material made by a mixture of other materials, for example, particles within a given matrix, particles of one material in a matrix made of other materials, and it has electromagnetic properties that might be very different from the properties of the components. So here's an example. For instance, if you have an insulator and you put a metallic these metallic lines, you paint metallic lines on them in the shape of these circles, like rings that are cut at some point. The rings work like if they were an inductance. If it is the interruptions of these rings, a charge might be accumulated there, so they look like a condenser, a capacitor. And then this system might have a LC resonance. And when the system is resonant, you have electric currents that go one way and then go another way, the opposite way along these circles, and that induces a magnetic moment. So even though this system is made of an insulator and a metal that might have no magnetic response, the complete system might have a magnetic response. So from the macroscopic point of view, it has some permittivity and it has a permeability, magnetic permeability. One can design this system so in a given frequency range, it might have a negative permittivity and a negative permeability. And in that case, electromagnetic waves can propagate through this system, but they propagate in a very funny way because it has a negative index of refraction. Let me tell you what I mean by this. It turns out that for these materials, the wave vector, which describes in which way the wave is propagating, the phase of the wave is propagating, is opposite to the Poynting vector, which describes in which way the energy is propagating. So in an ordinary material, if you shine an electromagnetic wave, part of it is reflected, part of it is transmitted, and the wave vector and the energy flux go in the same direction. But if this material would be one of these metamaterials, the energy flux would reverse direction, would go on the opposite way. Now, this picture is completely wrong because the energy, if I shine, for example, light from left towards the right, then the energy, the transmitted energy, must go away from the interface. So it must be moving right, not moving left. So I have to exchange the direction of the energy flux. And to that end, I have to choose the opposite wave vector. So if I change the normal direction of the wave vector, it turns out that a wave that is moving upwards is refracted into a wave that is moving downwards. So that is what is meant by negative refraction, because both waves are in the same side of the normal to this surface. Now, one can make other kinds of exotic systems, for instance, metasurfaces. A metasurface is a surface in which lots of particles are deposited with different geometries, like these ones here. You have this in the shape of the letter V, the letter L. This would be like an open L, and then a straight line. And then if this has a large index of refraction, it might happen that you have resonances in these particles where the light moves from one end to the other and then comes back in phase. So these resonances, when light goes across these particles that have resonances, the phase of the light changes. And one can use this change of the light to control the refraction of light as it goes across the system. So on a flat system, if you shine an electromagnetic wave in the normal direction, the wave goes through in a straight line. But if you manipulate the phase with this kind of particles, you might make the wave refract, and this refraction might depend on the color of light and might depend on the polarization of light. This can be used, for example, to build a lens, a flat lens. So this is what is called a meta lens. It's again built of many electric particles put on a surface, and you can set up the system so that light that shines on the upper part of the lens is reflected downwards, and light that shines on the lower part is refracted upwards, and then you can focus light on this point, and this is an image, an experimental image of how this light is focused. Another kind of systems are systems that are periodic. So here I have a periodic superlattice where two dielectric transparent materials alternate. At all of these interfaces, you can have reflection of light, and those reflections of light act coherently when the phase acquired is a multiple of 2 pi, an angle of 2 pi. Sorry. So these multiple reflections, what they do is a Bragg scattering of light. And Bragg scattering means that the wave vector can be changed by a multiple of 2 pi divided by d, where d is the period of the system. And that means that the light that would ordinarily follow a dispersion relation, frequency as a function of wave vector, that is a straight line, this straight line can get shifted towards the right. This straight line can get shifted towards the left. And this leads to these points where the two lines cross, and these points correspond to the degenerate states that can be coupled with one another and that have the same frequency. The coupling destroys the degeneracy and opens a gap. So if you, in a plot of frequency as a function of wave vector, actually it gets a curvature, and there appear these regions where light cannot propagate. So these are photonic band gaps, which are analogous to the electronic band gaps that appear, for example, in semiconductors. And of course, you can make these periodic systems in 2 dimensions or in 3 dimensions. In 2 dimensions, they have been used to build novel kind of wavelengths. So in all of these systems, the problem is that they have optical properties that depend on the composition of the materials. For instance, what is the material that makes this green particle, and what is the material that makes this blue matrix. But they also depend on the geometry, and the problem is how to calculate the properties of these systems. And what we have developed is a method to calculate the effective response of the system so that we can change this system that has a microscopic texture into a homogeneous system but with an effective response. Now, the effective response is not simply the average of the microscopic response. For instance, if you take this, would be the displacement as a function of the electric field. This defines the electric function, this epsilon, which is the permittivity. If you average this equation, you obtain the macroscopic displacement. So the macroscopic displacement is the average of is given by the macroscopic response times the macroscopic electric field, but the microscopic permittivity is not the average of the microscopic permittivity, as you would have to average this product, and the average of a product in general is not the same as the product of the averages. So that means that the average of the permittivity has no physical meaning. So what we have to do is find operators whose average does have a meaning. And there are many ways of proceeding. Let me show you one of the simplest ones. If you take the displacement field and project it into the longitudinal space of displacements, in a system that has a small scale, ignoring the retardation, the time that takes the field to propagate from one part of the system to another, then it turns out that this obeys the same equations as the external electric field. The curl of the longitudinal displacement is zero. That's the definition of a longitudinal field. And its divergence is the external charge. So it's unrelated to the texture of the system, and that means that it has no spatial fluctuations induced from the texture. So if I write the electric field in terms of the displacement field, instead of writing the displacement field in terms of the electric field, this is an equation that can be averaged, and since D has no fluctuations, it turns out that the macroscopic response is just the average of the microscopic response. So I don't have much time to explain this, but it is summarized in this phrase. The macroscopic response to an external excitation is simply the average of the corresponding microscopic response. If we take a simple system that has only two components, then the electric response has one of two values, either epsilon b, say, in a material that I will call B, or epsilon A in a material I call B. So one can describe the geometry of this system by a characteristic function, which is a real function that only takes two values, the value 1 and the value 0, when I'm in an inclusion, say in these green particles in the figure, or 0 when we are in the host, which would be the red region in the figure. So it turns out that the electric response that depends on position can be written in terms of the characteristic function and some complex number, which is called the spectral variable. So what we have to do is obtain the longitudinal projection of the response, invert it, and that is proportional to this operator here, where B is the longitudinal response of the Fourier transform of the characteristic function, and I have to invert this. So this is similar to what one is used to do in quantum mechanics, which is you take a Hamiltonian operator, which is a Hermitian operator, you subtract it from a complex energy, and you invert that. And then we have to take the average, and averaging is like taking the wave vector equals to 0. So we have to project this into the macroscopic state. So to do that, one can represent the operator using Haidok's recursion, which I will try to explain here, which is we apply whatever is our Hamiltonian to the macroscopic state, build a new state, orthogonalize that state to the previous state, and then that gives me, if I start with state 0, I get a state 1. If I repeat this procedure, from state 1, I get state 2, from state 2, I get state 3, etc. So the idea is to iteratively I apply my operator and orthogonalize. And then when I orthogonalize and then I normalize, I get these coefficients, which are called the Haydock coefficients. This is how you calculate it, it's just simple formulas. And the idea is that these Haydock coefficients represent whatever my operator is. It becomes a three-diagonal operator, which has zeros mostly everywhere. And this can be obtained by going to Fourier space and back into real space. They can be done very efficiently without needing any matrix operator. So in summary, we have a microscopic operator. The microscopic counterpart, the inverse can be obtained by first inverting and then averaging. And I show you just one example. And since I only need one element of the inverse, this can be obtained through a continued fraction. So this is the theory, and it can be extended beyond the non-retarded regime. So what I wanted to do is show you some examples. Maybe I'm already above time, so let me show you very fast. Here I have a small program that builds a characteristic function, so that you know what I mean by this characteristic function. So it is just lots of ones and zeros. Ones correspond to being within a particle, and zero to be outside of the particle. Here I will do the same, but for a larger lattice, which I won't be able to show as text, but I can show you as a figure. So in this case, I'm producing a circle. This is a pixelated circle within, say, vacuum. If I put many of these unit cells together, then I can get a crystal, which is an artificial crystal. And this is the metamaterial. So this will be a picture of my metamaterial. And then in my package, I can use this metamaterial, this picture, to initialize a geometry object. So from the characteristic function, I initialize a geometry, and as parameters, I use the characteristic function and the size of the unit cell and the direction of the wave vector of the light I'm going to use. I can obtain some attributes from that geometry. For instance, I can get the filling fraction of the system. I can get the reciprocal lattice and other properties that might be interesting. And then from the geometry, I can build a Haydock coefficient calculator. This would be an object. And I can use that Haydock coefficient calculator to build an electric function calculator. So this is the Haydock object I just built. And with that, I'm waiting for the calculation. I can actually calculate the dielectric function. So in this case, this number is the dielectric function of an array of glass rods. But I can do this also to get spectra. So let me show you a spectra. So now I calculated, this would be the dielectric function of a metal within the Drude model. And with that Drude model, I can, so what I'm doing here is with the Drude dielectric function, I use it to build within this map I built epsilon calculators using the same Haydock calculator I showed you before. And then I obtain the actual microscopic function, and I make a plot of these microscopic functions, which is what I will show you here. So here I show you the numerical calculation using my package, which is this line here. And the other line is actually the Maxwell-Garnett theories, an analytical function for this system that is approximate, but the approximation turns out to be very good. Now I think I will end this example here. What I did right now was just increase the size of my circles. I will show you in a minute when it finishes calculating. It took a few seconds. So what I did now is just increase the size, the radius of my circles, and what I have here is the actual numerical calculation, which is this the blue line here, and this would be the approximate result. So for this large fitting fraction of 0.64, now there is a discrepancy between the analytical theory and what is calculated with my package. There is a shift on the main resonance, and many other different resonances appear, which might be easily interpreted. So I guess I'm over time, so let me come back to the presentation. What I just showed you made you realize that the full spectra are as expensive and as calculating a single value. Furthermore, this can be parallelizable using this feature that's available in the Perl data language, and the fact that it is quite fast, the system, so one can tune resonances, absorption, reflection, polarization, etc., by modifying the geometrical parameters and calculating over again, since the calculations are not very expensive. So this is just a little bit about, I use the Mu classes and the roles because there are many different sub-packages that share behavior. And this is just for finishing, this is an example applied to an insect. The cuticle of these insects turn out to be made of fibers that are stacked one upon another, but with different orientations. This is called a Boolean structure. And we calculated the Green's electromagnetic Green's function of this system, which is given in this figure. And what is nice here is that you see that there is a gap. So there is a frequency range where no light can be propagated in this material. And that means that you have a very strong electromagnetic reflection. So that is the reason this looks like it has this metallic shine. But what is also nice is that this corresponds to a circular polarization. So this gap only appears for light that is circularly polarized. So that means that the cuticle of this insect actually polarizes light. So I'll leave you here with my conclusions. And I thank you very much for your attention. I'm sorry for taking more time than allowed.
Get to our questions.
Yeah,
really cool.
Thank you.
And it's really, from my perspective, hi, I'm John, by the way. Seeing what people are doing with Perl outside of web development, which is where I spent my entire career, is just really, really great. And I hope that the community can continue to figure out ways of integrating people like yourself and others who are using Perl in these kind of applications. I would hate to think that the next generation of scientists like yourself end up not using Perl because they didn't find a local community. So it's something very big to keep in mind. Thank you very much.
Thank you very much for the comment.
Dr. Mochán, can you hear us from the UK?
Yes.
Excellent.
Yeah.
Thank you for the fascinating talk. I've got some people here who are desperately keen to ask you a few questions, if that's possible, please.
Yeah. Can you hear me?
Yes.
Hello. This is Ed, aka Mohawk, the PDL maintainer. So just wanted to say hello. Thank you. I'm going to try to take some of the stuff that you put in your slides here and make a demo of it for Photonic. Can I make, so I'll email you about that. Can I make a request that you please release Photonic to CPAN?
It is in CPAN.
Not the latest version.
Yes.
I'll email you. It's fine. But anyway, I just want to say hello. It's great to see you and hear you.
Okay. Thank you. Yes, it's available in GitHub and CPAN. And currently the latest version is in CPAN.
He's checking.
Yeah, so it's a fascinating talk. Are there any other questions for Dr. Mochán? No. Okay, in that case then, thank you very much for your presentation.
Thank you.